Hello, today I'll be discussing how we can simulate Verilog-A files using Cadence tools. This talk will be divided into three main parts. The first part is how do you simulate Verilog-A files from the command line. This is because most of the time it might be much easier to simulate things from the command line because you're scripting things, so it's much easier to just simulate instead of having to use the graphical user interface where you connect blocks and all these sorts of things together, which can be time consuming. And also, like after you've probably figured out, let's say, the design, you might maybe doing incremental changes, and then it might be much faster to just have a script that just simulates the files from the command line. Maybe also some of the times, like maybe you want to experiment and things like that, so you don't always want to move to the command line, so it might make sense to do things in the ADE. So we'll talk about this next. And then finally, how we can use how we can reference external files from inside the Verilog-A file inside the ADE itself. So let's start with this first part here, which is how do we simulate Verilog-A files from the command line. So to keep this thing very simple, I decided that we are going to do a very simple circuit, but it doesn't matter whether the circuit is simple or not. The point here is to understand how we can simulate things. Because if I use something complicated, I mean, we might get bogged down in trying to understand what the code is doing, and we don't want to do that here. So we have this very simple RLC circuit, and as you can see, it has, I think, 1, 2, 3, 4 nodes, and it has an RLC. So keep this circuit at the back of your mind, so that because this is what we're going to be using in this talk. So now let's have a look here at, so I have already written all of the Verilog-A files for this circuit so that I don't have to type them, and this thing will not take too long. So the first part, so let me show you the first part. So, maybe I should come here to this part and then do something like that, this way, and then component. So as I said, I have a Verilog-A file, I have an RLC circuit. So let me just open these three files so that we can see them. So I have a resistor. As you can see, this is a very basic Verilog-A file. As I said, the point is to just understand how we can simulate things. So this is a very basic resistor. It just basically defines the linear resistor as V is equal to IR, and then it has a parameter called R. Then we go to the inductor, same thing, V is equal to L di dt with a parameter called L, and for a capacitor, we have I is equal to C dV by dt, and it has a parameter called C. So now we have our Verilog-A models of all of these components that we have. Of course, you don't need to use Verilog-A models to model things like resistor, inductance, or capacitance. These things are usually available directly from whatever simulating tool that you're using, but this is just to explain that yes, maybe let's say for some reason you decide to model a different type of capacitor, you can do it like that. This is just an example, as I said. So now we have the models of the things that we're going to be using. The next thing is how do we bring this together into an RLC circuit. So there are different ways we can go about doing this. The first way, since this is very simple stuff that we're doing, so what we're going to do is that we're going to connect all of these component RLC in the same way that we usually connect things like in Spice Netlist. So let me just show it to you quickly so that it's easier to see. So we come to the RLC TB. So I just created one RLC called TB. So here I'm connecting things using the Spectre language, of course, which is what's the default for Cadence. So basically, let's ignore this part for now. So as you can imagine, if you've ever written a Spice code before, you will notice that with Spice, you basically have your components, and then you decide what are the nodes that can be used to connect the component. For example, just have a look here. We have Vin, N1, Vref, and Vout. We can see them all of them here. Vout, all of these things. So let's have a look here at the first guy. So we're going to say that the first component, which is the first instance, is going to be V into N1, as we have here, V into N1. Then it's going to be a resistor of, here you can pass in if you want to change the parameter, if you want to do whatever you like, and then I1, you do the same thing, you give it the node names, and I2, or you do that, and then you, since let's say we want to do an AC analysis, so we have to instantiate a component, a voltage. So here I'm using V naught. Now I did not define V naught in the code. It's also of course possible that I implement V naught with a Verilog-A file, but as I mentioned previously, you don't always have to implement this basic stuff by yourself, because they are already provided, let's say, by the tool that you're using. So here I'm using the vSource that is provided by Cadence. And this vSource has parameters that we can change, such as the magnitude. So when you're doing AC simulation, you're basically interested in mostly two things: the magnitude of the AC signal and the frequency. And then we're specifying here that it's a sine wave, of course. Then after we've done that, so now that we have done this part, you have to, okay, we are instantiating components resistance 1. If you remember, these are the things that we had given the names to the module names of the resistors that we're going to be using. So we say RES1 and IND1 and CAP1. We need to inform the tool where to get these files from. So usually, if you have if you have done any Verilog-A in the past, there's usually one technique in Verilog-A whenever you want to okay, maybe this is not the part I should discuss that. We'll keep that for now. So in Cadence, the way to include the Verilog-A file is to use the command ahdl include, and then you specify the path of the file. Here I'm using relative path, which, as you can see from my test bench. So this is where my test bench is. So I go inside the folder called components, and then I can find my components. So I put them here, and then so we have informed the simulator where to find the components, the Verilog-A definitions. If you are wondering why am I using names like RES1, IND1, and CAP1, just so that you know, Verilog, if you use actually things like resistor or res without the one or something like that, because these are used internally by Cadence to represent their own resistor, the tool might complain, or it might be confused or whatever. So just make sure that you use some name which is not one of those defined names that are used by the tool. And now we basically, these are just like the sort of stuff that you do for every type of simulation. You say, okay, save all of my stuff, and then we specify that I'm going to do an AC analysis. It's going to start from 1 Hertz to 1 gigahertz and 20 points per decade, and we save the file. So this is very simple. And yeah, so let's say you have written everything. Now you want to simulate the file. Now before you simulate the file, sometimes let's say you've written your Verilog-A code and it might have a mistake in it. So first of all, you have to parse the files, your Verilog-A files, to make sure that there's no errors, and then you simulate them. So for example, here, this is my file. Now I'm going to show you something. So let's say I forget to put a semicolon here, and I close, I save the file. Now you might see that the tool is giving me some errors, telling me that compilation failed because of an invalid declaration. So basically it's complaining something like that. Now here I'm using NeoVim, and in NeoVim it allows me to run certain compilation scripts in the background, and then it parses the file and sends them here for me. So obviously not everyone uses NeoVim, so let me show you, for example, how you can do this from the command line. So I have so basically in the command line, how you would do it is go something like that. So here I'm inside this file again, 01. So let me maybe show you ls. So it tells me a components, yes. So I do ls. You can see all of my files: capacitor, inductor, and resistor. So this is the thing that I was using here. Now let's do cat so that we can see what we are seeing. I mean, what if it's the actual file? This is the actual file itself. So now the way you check the syntax of your file is using something like this. So since I don't want to copy stuff, so basically this is what you do. So to check the syntax of the file, you do something like spectre, then whatever these things mean. And so basically this is just the stuff that you just copy paste, and then you follow that with the name of the file. This is to just check the syntax of the file. If you want to do something even more deeper, Spectre has another option called ahdl lint, which gives you more information. Like it can probably you know, like whenever you're doing compilation, you do elaboration, you make sure that what you're referencing here is actually, even though it's syntactically correct, but it might not be the code itself. There might be some problems, like something might not be resolved and all of these sorts of things. So this one gives you more details. So for me, since I'm just interested at the moment in just checking the syntax of the file, I'm using this part. So let me just copy these. I hope my... Okay, I guess my simulation hasn't crashed. So we can do something like that. So I'll say Spectre DPL or whatever, then I give the name of the file, which is, let's say a resistor. That was what we were using. So as you can see, it says that it's reading the file, it's read the file and all these sorts of things, then no issues. So now let's introduce an issue, which is something like that. Let's introduce this issue, deliberate issue, which it gives me an error, and then let's do a cat again for the guy, and we see that indeed, no, it's not indeed. We're using, this is something else. No, this is, oh, I'm using for the capacitor, no wonder. So let's do this part, yes. Cat again, you see, I mean, so we can see that the semicolon is gone. Now let's do the thing I just told you just now. So you can see the same error that we are seeing in the code, like input pn. It's telling you that there's some syntax, and then giving you the line number so that you can fix it. Anyway, so this is just the part which I wanted to illustrate how you can do linting in syntax checking. So now that we are, let's say, happy that, let's say, we've checked all of these files, we're happy that this thing is how do you say, the syntax checking is the files are fine. The next step is to simulate the files. So we have to, let's fix this error. Yes, now we simulate this file rlctb. So now we go back to where we were, cd, then we see ls, we have this rlctb. Now the thing to actually to simulate the file is basically just Spectre, and then you give the name of the test bench, rlctb scs. You do that, then it's doing all of these sorts of things. It's now compiling, as you can see here. It's compiling each and every module. It's saving them as it's compiling them maybe to some binary, so that so that to make things much faster. And anyway, you can probably read through this, and it's obvious like why it's compiling it. So there's no need for me to elaborate more. So it gives me finally that we have no errors and all of these sorts of things. Now we will notice here that we have a file called .raw. This is the result of the simulation. So you remember here inside here we said it should save all of these things, and it should save things to a raw file. So now we have the raw file. This is what basically contains our plot data, and we would like to see what's inside the plot data. So now we have to launch Cadence own tool that allows us to view plot data, which is called Viva. So for me, I can do something like this. I think Viva, and then I do something like that. And then I just wait. It opens for me in a new workspace. So this is Viva, and then I can come to File, open Results. I look inside here. I do this part, which is the name of the file that we just generated, and here we can see the name of all the, let's say, the different types of simulations that we run. We run only AC simulation, and we give it the tag AC1 so that we can see it here. Now inside here we can see all of the signals that we that were saved. So for now we're only interested in Vout, so we can just move to something like yeah. So basically we can see do all the fancy stuff that you need to check 3dB, or use the calculator or something like that. But anyway, you get the point. So this is how you do your simulations from the command line. And let's close this. We're no longer interested in that. So this is the first way to do the simulations. Now let's go now to the second way. So now let's go to the second way now. So this is the first way that I just described, is we actually combine the files in this way. As you can see, we combine them like that. The second way that we can do these things is to instead of actually, we can create a new module that combines them in Verilog-A. So in Verilog-A, so basically this is almost the same file as the previous one. The only exception is that instead of bringing the things together in the Spectre language, we bring them together in the Verilog-A language. And Verilog-A language tells us exactly how we can instantiate modules. So basically, you give the name of the module, you pass in the parameters that you want to change based on the parameters that we get into this module itself. The instance, the label, we give the name in this module, and then we do the connections just like the same way again. So now when we have something like that, how do we go about creating our, we have to obviously write the test bench just as before. The only difference is that now we are instantiating that module itself. So we give it the name of the module, whatever, I0. Then now our module has 3 pins. So we assign the pin names exactly just as we did previously. Then we call the module, which is RLC, and then we pass in all of the parameters that we want to change, just like that. And then the rest of the code is the same. So, okay, this is the part which I probably should need to mention now. That, okay, now we are, as you can see, we are including all of the files that we are using in our simulation. So even though we are calling here RLC, right, ideally we should only include RLC and not the other subcomponents. The reason why we do this is because, okay, before we go to, because let's see here. So usually in this RLC file, if you're using standard, let's say the recommended, the standard way that you find in the manual itself for Verilog-A, they'll tell you that to include. Now here inside the RLC that I'm defining here, we have res1, cap1, and ind1. Now we need to reference these modules inside this file itself. So the recommended way of doing things is to do something like that, include the file itself, include something like that, and then you give the file name .va. So this is the standard way of doing things. However, Cadence does not like that. So they prefer that you don't include the file like this. They usually don't like to have more than one module per file, because the include statement just basically means include that module itself inside this file. So this will basically have 2 modules. This will basically translate to paste the content of that file here. But for some reason, Cadence doesn't like that, and probably they have good reasons for that. So the recommended way in Cadence is to just take all of the files and include them here. So this is why we are bringing all of the files here, just as before. And again, I just realized that I probably, let's see, RLC, so RLC2, so we should call this thing RLC. Why did I do it like that? Anyway, so just as before, we can compile this file and make sure that it compiles analog. What was that? Analog Spectre RLC-TB. Then, just as before, we just compile and we got the same thing. So, I can go open Viva Excel and show you that the results are the same, but you get the point. There's no need for that. So this is the second way you can maybe compile your files from the command line. I just wanted to bring to your attention that you can maybe combine the modules differently using either Spectre or using either the Verilog-A way. So now that this is out of the way, now let's go to the part where the second topic, which is how we can use this from the ADE. Probably this is the way that most people maybe would want to use Verilog-A, because maybe you're experimenting, you have different blocks, you want to bring your Verilog-A file into the GUI and then have a block and then move it around, all these sorts of things. So we'll go to that now. So let's go to ADE, and then inside here I can do again analog. This time we say run me, so that I can run these files. No, ch run me. Okay, so now we go to this part. Let's come here quickly. Let's wait a few seconds until this runs. Okay, now I can do this part. So let's now try to do exactly what we did previously, but now here in the command line. First method I'll use is the elaborate method. It's very long, but the whole point of these videos of yours, of course, I know that my videos are unnecessarily long sometimes, but the whole goal of these videos is to maybe go through the process so that even I myself in the future, when I've forgotten something, I probably will have to watch my video again. And then I don't want me to assume lots of things that I mean, I want when somebody watches this video, he knows exactly how to replicate it, and then it can be easily done. So let's start with just creating a new library. As we see, let's say example 1 or something like that. So then we don't want to attach anything. So now inside example 1 we have it like this. So now if you remember, we have all of these files that we did previously. This one's components 1, 2, 3. Let's bring them. So basically we're going to create them one by one by one, and I'm going to show you how we can mix different implementations together and how we can select one implementation over another. So for example, most of the time, let's say you use Verilog-A. You use Verilog-A specifically maybe because let's say you have a design in your head that you want to do, but you don't want to build the blocks in the design with analog components because it takes too much time. For example, let's say you need some operational amplifier somewhere and you don't yet know what are the requirements of this amplifier. So basically, you, instead of wasting a lot of time trying to just build several different versions of the amplifier, this one with this amount of, let's say, input dynamic range, output dynamic range, gain, or whatever, you write a Verilog-A file of an operational amplifier that models most of these behaviors that you're interested in, and then you can play with that Verilog-A file. Later on, after you are satisfied with your Verilog, with the result of your design, you start replacing your Verilog-A files with actual models themselves, with actual, let's say, SPICE stuff. So basically, this is the main idea. So this is the idea. So I'm going to actually go through this type of workflow so that we can have, we can see how we can have two different versions of the file at two different implementations of a certain block at the same time, and how we can switch between them easily. So this is the whole point of this part of the talk. Now let's start from the beginning. So we need, remember, 3 components: resistor, capacitor, and an inductor. So let's start from this. So let's say res1, we just do stuff exactly the same. So now let's take a resistor, and I do hide. So I'll rotate it like that. F. Again, we do it like this, like that. Again, it might sound like I'm actually wasting too much time, but actually there's a point in all of this so that we can see as we're doing things, how things maybe evolve and what we might need to do to change things. So now we have our resistor. As I said, we want to see how we can switch between different implementations of different things. While I was doing just now the simulations in the command line, I was actually using only the Verilog-A definition of the resistor. However, here I'm actually doing 2 different implementations of the resistor. I'm using the one as defined by Cadence, the one that you get, and the one that I've actually implemented in Verilog-A. Now, as I said previously, the whole point of all this is that just imagine this is something more complicated, like some op amp. So you have an op amp that you have designed using actual components, and then you have another op amp which you have designed using Verilog-A. So we have 2 different implementations, and then we need to use either of them in the design as we see fit. So basically that's the point. But just imagine that this is the most basic way of illustrating that. So now we have our resistor. Then we can probably so remember that every component that you use in your designs has input and output. I mean, not input and output, but it has, let's say, pins. So you have to make sure that if you're going to use a capacitor, like a resistor like this one, it has pins P and N. Your schematic view, or all views, or all implementations of that resistor have the same pins. So we will give it again the pin. So P and N, they have to match. Make sure. So we do input output, and then do something like this, and do something like that. So now we have our resistor. Very nice. Let's repeat the process for a capacitor. Do the same thing, hide this way, maybe something like that, zoom in, do it like this, do it like that. Again, our capacitor has 2 pins. Then we put PN, then we do something like this, we do something like that, we save, nothing, no problem. We do it again, inductor 1. I don't know if I have a hotkey for an inductor. No, because I rarely use it. So ind, yeah. Then we can do something like this, just as before. Then we do the pins again, PN, this way. We do this pin, another one, very good. So let's have a look now. We have capacitor, inductor, resistor, very good. And now we see that we only have one implementation at the moment for each one of these. We have a capacitor, it has an implementation which is given the schematic view, an inductor, schematic view, and stuff like that. So now we are going to bring our own implementation from Verilog-A. Let's go to, for example, let's start with the resistor. So again, you click on the resistor, you give it a new, then we say resistor, but now we don't want a schematic view, we want a Verilog-A view. So we say Verilog-A view, it asks you to type your stuff, so we type our stuff here, and then we do save. And now it asks me if I want to create a how do you call it, a symbol view. So the symbol view basically, because this is, if I want to use the resistor, it's currently in text. How do I use it in the actual, in the GUI? You have to create a symbol. So this way that we're doing it at the moment, it automatically creates the symbol for us. We can actually do the symbol ourselves, and then, how do you say, and then by using the pins in the symbol that match P and N, then it will automatically know that we already have a symbol for this thing. Maybe I should do it for another one, but I don't know if that would take too much time. But let's just accept that this is the automatic view that we get. We just use it because it actually simplifies the process a lot. So we go to P, then we just have P and N, and then we're done. So just like that. Where's the file? Okay, it's behind. Then we say okay. So now this is my, how do you call it? The representation of the resistor with just using 2 pins, P and N. So we can just delete this part because this part will, whenever you use the symbol in the ADE, it will tell you the instance name, like I0, I1, I2. Usually this is too much information for me, so I'm going to delete this part. You can modify how it looks like to make it look more like a resistor, but who cares about that for now? So we're going to accept this and then go to this part. So now, just to point out that we now have 3 views for the resistor. We have a schematic view, which is using the symbol, which is using the representation of the capacitor as given to us by Cadence. It has pins P and N. We have the Verilog-A view, which is what we defined ourselves, and then we have the symbol view, which basically represents the, let's say, higher level abstraction of what a resistor is supposed to be. So you get the point. And all of them have the same pins. Of course, if they don't have the same pin, then the tool will say, okay, how come you have a resistor, something, this is supposed to be like a module and it has different pins. So all of them have to have the same pins. Of course, it makes sense because you want to be swapping one for the other one. Otherwise, how can you have something with 3 pins and something with 2 pins? We do the same thing now for the, let's go to the inductor. Same thing, we come here, let's say, nope, I'm sorry for that. We do this part for the inductor, Verilog-A, yes. We paste the inductor code, just make sure that I'm pasting the right thing so that I don't end up pasting something wrong. Do you want to create it? Yes, we do the same thing. Just do the part, pin N. We can actually fast track this process. You can just copy paste symbols from different parts of the designs, and yeah, but we just have one more left, so there's no need for that. So we go to the capacitor, we do this part, and then we yes, again we open a new one, capacitor, we paste it here, save, okay. I'm happy with these so far. Save. Okay, you want to create it again. For some reason it decides to put both of the pins up. PN. Okay, so now we have the three different symbols, the three different components that we're going to use. So now let's bring all these three things together as an RLC circuit. So we do another RLC. So RLC. So we can, now for RLC we want to use the schematic view, which means that we want to combine them all together in the, let's say, the GUI. So RLC. Now for the RLC, we see that we come here, we switch to the library name that we are using, which is example 1. And then inside this library name, we see that we have all of the components that we had defined previously. We have a capacitor, inductor, and a resistor. So we can come here, resistor. You see, this was the symbol that we created. And let's go for an inductor. Again, we connect it like that. And then finally, we do in what's the other one? Yes, and a capacitor, so we can rotate it like this. No, something like that. And then we are almost happy. So this is an RLC circuit. This is, remember, this is supposed to reflect this thing here. So we can do it like that, just this way, this way, and then this way. Finally, we let's give these things pins. So why do we need to give these pins, you might ask? Because we want to also have a Verilog-A implementation of the RLC circuit. The whole point of all of these things is to just show you how you can mix match, you can mix lots of different things together. You might not need to do all these steps, but just to walk you through all of the different ways of doing things. So let's create a pin for now for these things, because we would like to instantiate this as a test bench. Again, pin, we go to VIN, remember the names, VOUT and VREF. So VIN, VOUT and VREF. Very good. So we do something like that, and then we are happy about this. No errors. Very good. So now we have an RLC circuit. Now let's have an RLC implementation using Verilog directly. So this RLC circuit, mind you, it is using, I mean, it might sound ridiculous what I'm doing, but let's, just so that we understand what's going on. I have an RLC circuit, which is using something called a resistor. And this resistor can be both, it can be either the one that is given to us by Cadence or the one that we have defined ourselves. And now let's say we also want to have an RLC circuit that has nothing to do with all of this, but it's something that we have modeled ourselves from a high level view. So we can go to this guy here. Remember this one here, this one. Where is it? Okay, I think I may have deleted it by mistake, but we can do that. But anyway, it doesn't matter. We can always type it ourselves. So let's maybe paste. Let's see, just 1 second. RLC, I don't have it here, so I can just new file RLC dot what's the name, VA. Yeah, so paste. Then we can start doing this thing called RLC parameter RC. I think I said 1 pico 5K, for example. Okay, so far so good. And then let me copy paste these things so that I don't have to type. Okay, I copied exactly the same thing that I had. Okay, let's do this. Where was I? RLC. And now I need a capacitor. Okay, so RLC. Now, since we have multiple statements, we have to have a begin and end. And then now we have to do these things. Now we have an RLC. It's supposed to have v in, v out, v ref. Then, yeah, so basically v in. And then we give an internal node called n1. And then it's from n1 to v out. And then it's from v out to vref. I might just maybe type it. It might be even faster to type. Okay. So now we have we created an internal node here called n1. Usually, Verilog-A, whenever you're using whenever you're using a node internally that you're not accessing, it allows you not to define it. But for some reason, I think Cadence requires you to define it. So we give it an electrical n1. So now we have our. Oh, I have lots of. Okay, I did not. So this guy's here, VI, I did not change VI this way, no, VI, this, yes. Okay, I think this should fix the code for now. Hopefully we have something that works, so we can go back to Cadence. And then now let's define our RLC again as a Verilog-A. Let's go to what am I doing? So we come to this part and then we do Verilog-A. Very good. Then we paste. We see that we have an RLC circuit. It has 5K, all of this fancy stuff going on. Okay, I'm happy about that. Do you want to create it? Let's create it. We do this thing called v in, v out, vref. Okay, no, not here. Bottom pin. Okay, so v in, v out, vref. So far so good. Yes, nice. Now we have to create a test bench to give it the inputs. So we do again RLC TB. Then what's the name of the? We want to use a schematic for that. So now we bring our RLC. Where's it? Oh la la. RLC, yes. So we have the symbol that we just created just now. Then we can start connecting. Then we put a ground here, for example. We give a sine source here, for example. And then we're almost done. Copy, paste. This way, this way, this way. We can give this in, out names for these nets. Oh la la, another mistake. In, out, this way, this way. Now let's give our source an AC magnitude of 1, just as we did before, and then the frequency of, I think, what was the frequency before? Let's remind ourselves. It was frequency was 100K. Okay, 100 kilohertz. Very good. So now that we have our everything, now we save. Let's see if everything's fine. Okay, it's telling me that I have floating nodes. We don't care about these things. Apply, save again, no more errors. So finally we have everything ready for simulation. I hope it's not the most confusing thing in the world. The whole point of this is just to show you how we can have different implementations of different things. So let's maybe go through it one more time so that it's clear what's going on here. We have an RLC circuit. Good. This RLC circuit has two implementations. One implementation is shown here, and the other implementation is the Verilog-A file. Very good. Now the Verilog-A file is standalone by itself. The implementation that we have here, it itself has different implementations. Internally, it has an RLC, and each of these things have their own implementations. This resistor is implemented again 2 different ways, the same for these other things. So now we want to specify in this. So now we have this test bench. Yes. So this test bench, basically, we need to tell the tool what exactly we want it to simulate for us. So this test bench contains all of the information that we have just created just now. We want to be able to know, to tell the simulator, okay, now simulate for me either the Verilog-A of the RLC or the schematic of the RLC. And then if we choose the schematic of the RLC, we want to also tell it that please choose the Verilog-A implementation of the resistor, or the schematic implementation, or the Cadence version of the resistor, and stuff like that. So to manage all of these things, there's something called a hierarchy editor in Cadence, which makes life much easier. So while we are still selecting this RLC-TB, we can create a new view, which is called the configuration view. So the configuration view, you can see that one here. I just type C so that I don't have to look at this config view. Something like that. So we have a config view. This config view is where we configure what exactly the simulator is going to simulate. So we select OK. We're in the library example 1, RLC-TB. Now for inside this RLC-TB, we only currently have one view, which is a schematic view, which is exactly what we want. We click that one. So here you can put all of these sorts of stuff, but luckily we can use a template, and then if we're using Verilog-A, we just simply choose Spectre, and then it populates for us all of these things. It tells us, for example, what are going to be the default views of the instances and stuff like that. Anyway, you get the point. Click OK. So now we see all of the components in the design that we're using. So we see that we have cap1, int1, res1. Then we see that so these are the things that we have defined in schematic, yes. And then we see that we have also the RLC, that's right. And then we see that we're using things from Cadence itself, which are the capacitors, inductors, resistors, and then the sine wave. Now this view just gives us a very rough idea of what's going on inside the design. To get a better understanding of what's happening, we have to go to the tree view. Now this tree view, let me open this part here. No, we cannot see that. So this tree view, it tells us that we have a main block called, let me move this guy here. Maybe we can see this main block is called the I0, which is this guy here. If we click on it, this I0. Now this I0, it has two stuff. It has two things going on. It has the I0 here and it has V0, which we can see. And then inside this I0, if we go inside this I0, we can place this, just do it like that. We can see now internally we have this. You can see that as I'm pressing on it, it's doing that. Then we have I0, I1, and I2. Very good. And then inside this I0, furthermore, we also have another component. So this R0 that you see here is basically the schematic view of the, because at the moment we have schematic chosen. So it's referencing the Cadence implementation of the resistor, stuff like that. So at the moment, because of this view list that we have here, and the default, it's selecting all the Cadence implementations. So let's so as you can see, we have schematics using the schematic view of all of this stuff. Let's say we want to do that for now. We can click save, and then we can open ADE Explorer, which is basically the place where we're going to define what simulation we want to run. We create a new, since we haven't done anything yet. We do something like that. So let's keep this guy open for now, so that we can play with it anyhow we feel. So now we can, first of all, let's output. Let's say we want to plot, select on design. I would like to plot this by V out, because usually when you are doing RLC, we only want to see the output, let's say for now. Then the analysis that we want to run, it's okay. For some reason, you always have to switch the simulator, even though we're doing Verilog-A simulator. We don't want to run analog mixed signal because Verilog-A is basically analog. So we switch the selector, we switch this thing to analog again. So we have switched the simulator to Spectre, and then now we go to analysis. We specified that we want to do a transient analysis, and then for how long? No, not transient, AC analysis. We want to sweep it from 1 to 10G as we did here, 1 to 10G and 20 points per decade. We click OK. So now we have everything that we need. Now we can do, let's see. So we can actually see the netlist that we get. The way you do it, go netlist, you see create or recreate or whatever. So now it tells us exactly everything that's going on. So we can see that our RLC, this is the guy. It creates a subcircuit for us, RLC, because we created something like a symbol for the RLC, and each and every one, these are the internal implementations and so on and so forth. You can have a look here. So we can see that there's no thing called AHDL include in this netlist because it's not using any Verilog-A implementation at the moment. And then these are the instances that we see. I0, it's choosing RLC, and then in, out, whatever, and then V0, this is the voltage source that we provided, and then these are the various simulator options, and then finally it runs the AC simulation, and then with lots of other stuff going on. So with this done, we can save, and then we can run our simulation finally. So we run this simulation, and then we see we have something like this. Very nice. I mean, almost the same as we have before. So now let's switch. Remember, this guy was schematic. This is the top view of the RLC. Top view has two implementations. It has the RLC, it has the schematic view, and then it has the Verilog-A implementation. So now we go to set instance, then we go to Verilog-A view. So notice that as soon as we say Verilog-A view, everything else disappears. Now we come to this. So we see that this guy is giving us, telling us that we need to recompute the hierarchy. This is usually, you always have to do this after whenever you change the instances that you're going to be using in the simulation. Then you have to recompute the hierarchy. Then you say you accept that, yes, I'm happy with that. So now we see that everything is almost gone. So basically we're only using now VCN, the sign source from Spectre, RLC from Verilog-A, and the test bench basically that put these things together. So now we're happy with this. Then let's run the simulation one more time. So as soon as we have done this, now we are basically doing something else. But in fact, let's recreate the netlist so that we can see the difference. So now we can see that, yeah, basically we have almost the same thing as before. I0, RLC, whatever, the sources and all of these things. Now it's saying that please include the content of that RLC where we are defined. So now it's not including it here directly. So it's saving the definition of the Verilog-A implementation of the RLC that we pasted. This one here, where is it? RLC, this one. It's basically saving it in this location, which we can click, and then we can see the file. So it's basically using AHDL include just the same way as we had done something here. Now we close this, we run the simulation. Now I want you to pay attention to what we are have a look this thing here. Let's do this part. So run. Now let's pay attention a little bit to what we see here. Okay, you see that there is a difference between the simulations, right? Because the difference being that if you go again to the netlist display, you see that in the netlist itself, it's telling us that it's using R of 5000, whereas when it was doing the simulation using the schematic view, it was not using R 5000. Now, if we go to this part here, I mean, this is something that you have to really be careful to make sure that you are doing things correctly. Otherwise, you might be using values which you think you might be using, but you're actually not using. So we did the simulation with the schematic view. We had one plot. We did the simulation with the Verilog-A view. We had a different plot. Of course, if ideally both of these two things should be the same, but they're not the same. So let's go to the this view, and then let's have a look. So this is basically the test bench that we are simulating. We can click yes. So we can you see for sure that it's the test bench itself. It is telling us that we have RLC, and the R that is using is 5000, and this is L, and this is C. Very good. But then when we do this, let's switch it again to the schematic view. Let's remove this none. We're back to the schematic view. Run the compute the hierarchy, whatever. Yes, and then we come here. So this, as you can see, the Verilog-A, it's telling us that yeah, we are using RLC on all these sorts of things, but then when we do the simulation here, it uses something different. It uses something different. So in fact, what is it using? In fact, it's using the default, the value that we had specified here for R, which is where is it? R, which is it is using the R, which is using 1K. So which means that it is not inheriting the 5,000 that we had defined higher up in the hierarchy. So this is something that you have to really be careful about, and if you are not careful, you might actually be changing stuff here. Changing stuff where? Here. Where is it? You might, I mean, I have no idea anymore where I am. You might be changing stuff here, and things are not reflected underneath. So what you need to do is, you have to specifically, explicitly tell the simulator to pass these values from the top view down into the bottom views. How do you do that? You do that with something called, this thing's called p-par, and then you specify the name of the variable that you want to pass down. So let me just show you for now. So usually, so right now, when we have this thing called the RLC, you see that it has these things called CDF parameters. It has three things called RLC. So when we compiled or imported this Verilog-A view directly from, how do you say, from when we imported it, Cadence was clever enough to say, okay, I mean, you have parameters. It detected the parameter that we have RLC, so it created for us things called CDF parameters. So these CDF parameters allows us to modify the module that we have created so that we can change the way it behaves. However, if you create a symbol view from a schematic view, you will not have these things by default. You will not have parameters by default. You can do that yourself using something like this part, tools, CDF, then you go to edit, then you specify whatever you want to do. This is how you would do that yourself. If you want to create, let's say you have created a module, you have created, let's say this was a resistor with Cadence implementation, an inductor Cadence implementation, this with the implementation, and then you create a cell view of this using create cell view from cell view as just before. It will not have something like this. It will not have this. Then to be able to modify the parameters, the internal parameters of the module itself, you will have to go to this option, CDF and stuff like that. However, since we are using, we brought in from the Verilog, we imported the Verilog-A code, Cadence automatically defined it for us. So because we have the CDF parameters here, we don't need to create them ourselves, which saves us time. But these parameters do not get passed down to the children nodes. So we have to explicitly pass them down ourselves. So how do we do that? We come to this part again. So this guy, we go to R, do we see? So this guy himself, okay, I think this is because I was, just one second. Let me just close everything down so that we don't, we see. So now let's go to the, so let's go to RLC. Again, this is the RLC. We do schematic here. So we see this guy. So we see Verilog-A. So here it's telling me R. The R that it's reading here, it's the R from its own Verilog-A file, this file that we pasted, which was 1K. But now we want to overwrite it. We want to say, don't use your own 1K. Use the one that comes from above. So we do that with something like p-par R. R is the name of the parameter that's defined for the top module, that the symbol from the one that we got in the symbol view. So we say something like, then we do it from this way. For this one, we use the one with the L. Then for the capacitor, I hope this part is not too confusing, because it might sound like it's complicated, but it's not. So now we are passing from where was I? RLC TB. schematic. So this is the top view. We have RLC. We are basically just saying use those RLC that you get from the top instead of the ones that you had initially defined. Now we're done, we save this guy. Then we have to do it for the schematic views themselves. So we go to the, let's say, start with the resistor, schematic here. So here you can see that its R is specified as 1K. If we do the simulations right now, it will still be 1K. There's no reason why the R that we have defined, I mean, there's no way that this can tell that the R that we are using over there is supposed to be the R here. So you have to explicitly also tell it. So we do something like that. Yes. And then again for the inductor, we do something like this. And then for the schematic capacitor, we do something like that. Very good. So now, hopefully, whenever we change something at the high level view here, it doesn't matter anymore whether we are using schematic view, Verilog-A view, or whatever. All of these values get propagated downwards. Let's see, hopefully, now that this has worked. We go again to the config view. We say open, whatever, open please. No? Okay. Now first let's do the simulation using the schematic view, which is what we have at the moment. Yes. Then we do ADA Explorer. We already had one created, so we just click open to open the previous one. Then we can run the simulation. We wait a bit. Simulation completed. Very good. So now if we switch to the Verilog-A view, first of all, let's see the netlist that was created here. Display. Okay, very good. So you can see here that all of those values, the p-power that we had provided, it's now, if you know anything about how do you call it, Spice, you know that they have this way of indicating when you're passing things down. So let's see. So you see now that we are passing this value. You can see that we are passing these values directly down from down. But anyway, let's just confirm that we are doing the stuff correctly. So now we have this Verilog-A view. Previously it was completely schematic. Now it's completely Verilog-A view. Yeah, we can do update. Yes. Now we run our simulations one more time. Hopefully nothing changes. Hopefully nothing changes. Very good. Nothing has changed. Very good. So this shows something that might be very important if you are mixing lots of different views in your design, and you might be changing things from the top view and it's not reflecting in the lower levels of the hierarchy. So we come to, I mean, obviously you can, so previously we had done all schematics, all Verilog-A. So now we have schematic view. Now we can specify that, okay, for the inductor, I only want a Verilog-A view. That's it. So that's it basically. Just like that, you say update the hierarchy. We compute the hierarchy, yes. So here we have specified to use only the Verilog-A view in this part, and then we can see the run simulation. You will see that it only has one. I mean, nothing has changed, of course, because both of them are using, both of them are implemented in the same way. Let's see now the netlist display. Okay, we should see that AHDL include, it's including only the one for the inductor. You can see, because that's the only one we did to make sure that we are doing, to show that we're actually doing something correct. We can do for this, yeah, do it like that. One more time. Let's do simulation, netlist, recreate. So now we have both of them for the resistor and the inductor. So anyway, this is how you do simulation with different blocks, with different implementations of different blocks in using with the Verilog-A and mixing it up with an analog, with let's say an actual analog implementation. It was really too long, but it was, I think it's necessary for me to have gone through all of these steps and maybe show you like what are the pitfalls that you might expect if you're doing this yourself. So now that we have, okay, let's go, let's see the last topic. So we have covered this first two. Now you might be asking yourself, do I really need to always, let's say I am just interested in the RLC circuit from the Verilog-A, this one, right? I'm just interested in this. I'm just interested in this. Do I have to really define? I mean, I don't want to actually redefine how a capacitor. I don't want to actually switch between different views of a capacitor, switch different views of an inductor. All I care about is this one. So, for example, let me give you a more concrete example. Let's say you go online and you find a very, very nice implementation of an operational amplifier. Now, the operational amplifier will be some file like this. Now, inside this operational amplifier, for example, it might be broken down into different blocks. Like you have the input stage, output stage, whatever stage. And the file might come with 3 different modules. A module for the input stage, a module for the output stage, and a module for something else. The reason why they do that is because the output stage, for example, that you connect to an op-amp can be also connected to different other types of amplifiers, for example. It doesn't matter. So to reuse the code, you split things up. The problem is, you have now 3 different files, modules that are defining the behavior of one file. The question is, how do you bring all of these 3 files together inside the ADE environment? If you're trying to do this in Spectre in the command line, it's very trivial to do. But if you're trying to do this here from this ADE environment, it might not be trivial to do. Why? Because, let me show you, for example, let me show you, maybe it's easier to show with an example. Example 2, very good, do not process this. Let's go to this part here. So we do something like that. So let's say RLC one more time. Say we do, we call it 2, schematic. No, it's not. Is it schematic or Verilog-A? Verilog-A view. Just one second. So now we have this RLC schematic. So this one here. Let me call it 2. So somebody has actually implemented for you some very fancy RLC circuit. And this RLC circuit comes in 3 different files. And these 3 different files are defined and we bring them like this with a, how do you call it, with instantiations. And then you decide, now let me copy this into, you copy this guy into here, right? So the problem is, how do you, previously when we were doing it here, we had to define in this part called AHDL include, and then we included the components. But now we're not going to be defining the simulation files ourselves. This is something that gets generated internally. So how do you tell the tool that where are the definitions of these things? Now, the first way I actually try to do this myself is to just use that include statement, something like that. Include statement. It doesn't work because, as I said, Cadence does not like the use of include statement in files. So, which means that we have no way of doing this part here. Let's do this cap2. Let's do this way. So the way actually to do this is actually simple. So right now we have this RLC circuit, and then we can do it like that. We want to create the symbol. So luckily, it did not complain that it does not know what these things mean. Right? Because right now the tool has no idea what these things mean. So we can say yes, create it. So now we do the same thing as before, v in, v out, v ref. Very good. Oh yeah, I did a mistake, I think. Of course I did a mistake. This way. I'm going to delete the symbol view. Hate it when I put one of the pins up for no reason. Create it. V in, v ref. Is it v ref? Nope, it's v out. Then bottom pin is v ref. Okay. So same as before. do it like that. Save. Okay. So now we have our Verilog-A view just as before. But now we don't have to include, we don't have to define what's my R, how is my R implemented, how is my cap2, how is my in2, how are these things defined. So now we can use them. Let's now create a test bench, RLC 2TB, for example. We can say this is schematic view, then just as before. Yeah, we do something like this. Then we do this example 2. Then we do where is it? Yep, RLC2, something like that. Then we give it the ground like this. Then we do the connections just as before. We put here 1K, where is it? Amplitude, AC amplitude is 1, and frequency is 100K. Good. Save. We're going to get a floating error. We just press G and then we do this. Good. Very good. So now we do our test bench just as before. Explorer. So notice here we're not doing a config view because we're not switching between lots of things. The whole point of this section of the tutorial is not to show you how to simulate Verilog-A, but to show you how to simulate a Verilog-A file that has dependencies on other files. So we go to create new. We have not created one yet. We do this part. Now we go to outputs to be plotted just as before. We set things up. Then we do analysis. Nope, is AC 1 to 10G. Then logarithmic and then 20 points. Good. So now let me show you like the point that I am trying to make. So we do the simulation. Of course, it's going to tell us that what the hell are you? There's no. These files do not exist. It's telling me that what are these files? The instance R1, C1, and L1 do not exist. So the question is, how do we add these files? So, you might think, let's try to just bring the RLC files again here, just as we did before. But that's completely unnecessary, to be honest, because you don't want to go through the process again of redefining of. You don't want to go to create an R and then a C and then an L or all of those sorts of things. It's irritating, to be honest, to do that. There has to be a way to make this part. So as you can see, we are using res2, cap2, in2. So the thing is, how do we include these files? That's basically the question. You come to this part, analysis. Now you see setup. Usually, there's this thing called model libraries. Now model libraries, if you do something like this, let's say go to model libraries, then we go to let's go to one step back. Let's say, where was I? Parent directory, CMD. Let's do this part and say C3, this part. Let's include these files, as you might imagine. This is the most obvious way you can think. Include these files, then do that. However, notice that now if you do simulation, netlist create, it includes these files as regular files. It does not specify that these files are Verilog-A files. Usually for Verilog-A files, you need to use the keyword AHDL include, which means that if we run the simulation, it's going to be wrong. So you might think that for some reason there's a way to include Verilog-A files. So we come here, let's say setup. You start seeing, okay, this is not the way we can include Verilog-A files, so we have to delete. This is not going to work. Now then you say, okay, there's something else you can do, which is called the simulation files. So yes, so there's something called include path, whatever. So for some reason, none of these actually can do AHDL include. I actually searched online and couldn't find any better way. Somehow, this method works. Let me show you. So I come to this, so I go to CMD, I ISO 3, then I do this part. So I create a new file called ahdl files.scs. Now inside this file, I basically say ahdl include, ahdl include, ahdl include, and then specify the components here, these guys, these things. So that's all. So here I include my ahdl include, and now I do this thing again. I go to model libraries, I do this part, back, parent, include SSC. So now you can see now the net list to be plotted, to be saved. No, where my simulation, net list, create, recreate. So yes, now it includes this file, but this file is interpreted differently from before. Before we included a Verilog-A file, which was wrong. So now you include a, how do you say, a Spectre netlist, the Spectre configuration file or whatever they're called, and then it gets read correctly. So if we do this thing right now as it is now, so we can now run this part. Now it's going to compile the files and then hopefully it runs. So this shows you that yes, it's very easy now to just, how do you say, so compare this to the previous one. You can definitely tell that this is way faster to do. So basically you just bring in your Verilog-A files that you define externally, and then you include these files, and then you're done. So this shows you, like, let's say if you want to use some modules that you get online from somewhere, and it's defined in different blocks. You don't need to go through some jujitsu to somehow stitch it together inside the ADE. You can just paste the top module here, and then you reference the other modules inside a file like this one, and then you include it during the simulation, and then you're done. So I guess this brings us to the end of the video. I know that it's ridiculously long, but for some reason this is how I like to make my videos. They're supposed to be standalone, and then you're supposed to watch it and then go through the whole process. Maybe even after a while you've forgotten most of the steps, so you can be reminded of them. I mean, I do these videos as much as I post them online, but they're also for my own benefit, because after a while I usually forget some stuff. Then I start having to Google and all of the sorts of things, and then I remember, okay, I knew how to do this, but now I can't. I've completely forgotten. So yeah, I guess it could be made much shorter than this, but who cares? So I guess that's the end of it.